ester is formed by a condensation reaction between these two guys. What are the products of this reaction? Well, I would just draw it out and then figure out what you've got. So you've got CH3, CH, C double bond O is up here, okay, which means that we're then going to be very careful about how we put the rest of it on. Here's my C with an H, and then this carbon has a carbon and a carbon. Okay, now if you do that full kind of drawing out, it makes it a lot easier on you in terms of just reading it through. So you've got to find the one that fits. Okay, this final structure. Okay, it is this one here. CH3, CH2, C double bond O, C. It's obviously attached here, and then the H, and then we've got the CH3, two of them attached, given it like that. It doesn't have to give it that way. It's actually probably slightly incorrect, because what you would normally do is you would leave the hydrogen there and make that your, so just make the carbon on the other end. So you just would have put this as being CH bracket CH3 and then CH3 at the end. So your other thing though, you have to be careful of, because obviously this is also somewhere else. Oh yeah, here's NB. Okay, you have to recognize that you had a hydrogen and a chlorine, so it's hydrochloric that you make. Okay, so this is an acid chloride producing an ester, which is much faster than doing it with your alcohol and your acid. However, you know, fuming clouds of hydrochloric gas is generally not a fab idea. Question 15. Okay, secondary amines react with some carbonyl compounds to form unsaturated amines known as enamines. Okay, we've got a little picture here. Which carbonyl compound would react with CH3,2NH to form the enamine with the following structure? Okay, so we are trying to basically block this back in to what we've already got there. Okay, now I did quite a lot of doodles to make this make sense for me, but basically I'm just trying to find my R1s and my R2s. So your N, which is fine, your N here, sorry, here, is CH3, so that's that one there. Okay, so this is your R3 and R4 on this one. No use to you whatsoever, because that has got nothing to do with the carbon compound, which is what you're trying to figure out. Okay, so get to your carbon. Here's my carbon, and here's my carbon on the enamine. Okay, and then I've got my double bond CH. So here's my double bond CH. Here's my double bond CH. So the other thing that's attached to that is an R2 group. Okay, so this R2 is what's attached down here. So I've got a CH3. And my R1 group is up here. So my R1 group here is also, don't know why I wrote R1 there, is also a CH3. So when I redraw this now, I redraw this first compound but with R1 and R2 resubstituted. So R1 is CH3 to carbon, double bond O, bond CH2, and our R2 group is another CH3. So 1, 2, 3, 4, bute, carbon in the middle with a double bond O, so bute and O. There you go. Just take your time on those ones. Question 16. Which of the following functional groups is not present in warfarin? Okay, so we're just going to know your groups and work your way down. Okay, carbonyl. I'm looking for a carbonyl group, which means I'm looking for a C double bond O. Well, here's one in here. C double bond O. I'm not entirely sure I would take this one up the top here. C double bond O, bond C. So I've got an ester link in here, although the C double bond O is still a part of that, but carbonyl group definitely down the bottom here. Okay, carboxyl, however, I can't find. Okay, because you have to be very careful. This one here is C double bond O bond CH3. Okay, remember the hydrogens have just vanished from skeletal formula, so you're just expected to know that they exist and that they're in the right place. Okay, right, so carbonyl definitely there. carboxyl is not, hydroxyl, just be clear, is here, and phenyl group, this is a phenyl group. So it's a benzene ring that's had one of its hydrogens removed to put it on as a substituent group. Okay, so carboxyl is your one that's missing. Question 17. Which line in the table is correct for a high resolution NMR spectrum of ethoxyethane? Okay, and you've been given ethoxyethane, so that's nice of them. They didn't ask you to draw it from scratch. Right, number of proton environments, that's your first start. So proton environments, let's go with a colour we can work with. Right, let's go with the CH3 proton environment. Okay, that is actually identical to this CH3 proton environment as well. Okay, all of those hydrogens are in exactly the same kind of chemical conditions. Okay, and this CH2 is identical to this CH2. So we only have two environments. So basically C and D are out of the running. And then we're looking for the splitting patterns. So let's consider, well, we've only got to look at two environments. We'll just let's look at this these hydrogens first. Okay, so this hydrogen is next to another two hydrogens. So I'm expecting that this peak here will be split two more times. So I will get a triplet. Okay, this hydrogen set, so the green ones, they are next to three hydrogens, so they become a quartet with the split. So we've got a triplet and a quartet, giving us A as the correct answer. Question 18. Which of the following amines is likely to have the lowest boiling point? Okay, so two things really affect your boiling point. One is mass, but there's no difference between the number of carbons in here. Basically, that's not going to be a thing. And the second thing is intermolecular bonding. So your strongest intermolecular bond that could, or attraction that's going to be causing an increase in boiling point is your hydrogen bond, and that's normally what we're looking for amines. However, as you go down through the amines, primary, secondary, tertiary, when you get to the tertiary amine, you lose your hydrogen bonding. So in D, that's what we've done. Okay, it's become 2 carbons, nitrogen, and 2 carbons around that. So basically no spaces for a hydrogen on here at all, so this nitrogen has just got dipole-dipole stuff going on with the carbons. So likely to be the lowest boiling point would be that one. Okay, question 19. Ethane can be prepared by adding iodomethane to sodium. Little picture or reaction mechanism. When a mixture of iodomethane and iodoethane is used, the only alkanes produced will be. Okay, so what we've got here is a substitution reaction where we're taking out the iodine and basically attaching the two methanes here. Okay, so we've got potentially methane attaching to methane, giving us ethane. We could also have a methane and another ethane, giving us prop. Or we could have eth and eth, giving us bute. There we go, either a 2, a 3, or a 4, because our combinations are 1s and 2s, and hence the answer is C. Question 20. Which of the following will react with lithium aluminium hydride but not react with toluenes? So what I'm looking for on this one is recognition that you should know that this is your reducing agent. Okay, so this reduces, so that would be you going back the way from a carboxylic acid to an aldehyde back to your primary alcohol, or a ketone back to secondary alcohol. Toluenes, you should recognize even from higher, okay, that is an oxidizing. Okay, so if you're oxidizing, we are looking for it going from either a primary alcohol to aldehyde to carboxylic acid, or your secondary alcohol to ketone. So I want something that will reduce but not be oxidized. So reduce but not oxidized means I'm really looking for either carboxylic acid, because that's at the end of the primary chain, or ketone. Okay, so, well, here's your answer. You can draw it out. There's a ketone. Okay, This one, being very good, because obviously we've got HO at the end rather than OH, so that's an aldehyde. So that could do both. It could either be reduced back to a primary or it could be oxidized to carboxylic. Your C is an ether, because you've got CH3O, CH2, CH3, so it's not that. And D is a primary alcohol, so it's basically not got anywhere to reduce to, although it would be oxidized. Question 21. 2 substances were analysed and found to have the empirical formula CH3O. From this information, it can be concluded that the substances, so be very, very careful here. So, okay, isomers. Isomers have to have the same molecular formula and a different structural formula. If they're structural isomers, obviously you know other ones now with stereoisomers. This is empirical, it's not molecular. You don't conclude that they are isomers because you don't have a molecular formula. Have the same molecular mass, exactly the same argument that you have with the isomers. You don't know if they are actually exactly the same or if they're just multiples, so not the same molecular mass. Have the same functional groups? No, because you don't know how it's set up. They could be isomers of the groups, so it could be like an alcohol in the ether. You know, it's quite possible with that kind of formula. So no. Have the same percentage mass of carbon? Definitely, because this is the ratio that you've got down to, so that percentage for carbon will be the same. Okay. Right, question 22. The wavelength associated with the spectral line of hydrogen can be determined using following relationship, and you're given a formula. And then you're given information. And you just have to plug it in. I don't know why this has been given us. I suppose it's just to do with how complex the numbers are for you guys. So it's 1 over lambda. We've got R. In fact, I'm just going to substitute it in as we go. So 1 over R, so 1.1 times 10 to the 7, okay, from here. And then we've just got to be really careful with our brackets. So 1 over N1 was it says N1 is the energy level to which it falls, and it says it falls from the 9th to the 2nd. So I'm going to do 1 over 2 squared, okay, minus 1 over, it fell from the 9th, so 9 squared, okay. Now, first time I typed this in, I got some numbers. I didn't keep it all in the calculator, and so I ended up with it not going to exactly where I wanted it to. So it's still not perfect if I write it out what I've got, because if you keep it in your calculator, it's better. Okay, so here we go. This is my answer at 1 over lambda. Okay, so to get lambda, I'm just basically flipping this. So 1 over this 197.531 got me pretty close. I got to 3.82 times 10 to the minus 7, which is good enough for me to say it's 3.83. Okay. 23. Low res proton NMR for an organic compound is shown below. Now I've pulled in a little bit of the proton NMR spectra chart from the data book, but actually you didn't really need it once you'd figured out what's going on here. Okay, so we're asked which of the compounds gave the spectrum. You've got one shift. Now that's the most important thing for you to recognise. Only one shift means there's only one proton environment. So if I start drawing these out, okay, here is propane. Okay, so proton environments for propane, these guys and these guys are in exactly the same proton environment, but these two in the middle are in a different proton environment. So there are two, so it can't be that one because we have only one. Okay, propanol. We're going propanol, double bond, and hydrogens. Oh, sorry, extra hydrogen there shouldn't have. There we go. Right, so this is, you can tell almost even when you're starting to draw that there's way more. So this hydrogen is in an environment all by itself. These two guys are in a different environment, and these three are in a different environment. So 3 different environments, there's no way that that can be the same or the right thing. Propanone, see, with your double bond in the center. Okay, this is your winner, because these 3 hydrogens are in exactly the same position as these 3 hydrogens. So they give me just one environment, so that's the only possible answer. Okay, and I'll just show you propanol in a minute, but also this is somewhere around about 2.2, something like that, and that was a propanone. The shift, however, is not particularly helpful, because here's your shift pattern that you're looking at. Aldehyde, ketone, acid, ester and amide are in the 2.7 to 2, so it fell reasonably. So I suppose you could almost get rid of the alcohol, because the alcohol is at 3.9 to 3.5, so it's actually too far, but I think you're as well just doing it the other way. So basically looking for your proton environments in that one. And again, same issue. You have way more than you want to have. You've got 1, 2, 3, 4 environments in this one. So propanone is your only possible. Right, question 24. Which of the following contains the greatest number of negatively charged ions? Genuinely feel this is a little bit of a gift of a question, because it's just being careful. Okay, so what you have to first identify in each of these is where the negatively charged ions. So here is a negatively charged ion, that's the nitrate, and you'll notice there are 2 of them. That's important. Sulfate here, there's only 1 of them. Chloride, 2 of them, and iodide, 1 of them. So the only thing that is tricky in this is remembering to put a multiplier in, okay, for the negatively charged ions. So the first one, I'm just going to use N equals CV for the whole lot of them. So first one is going to be 0.1 times 0.4, so 0.04. However, there are 2 negatively charged ions in each of these formula units, so times it by 2 means I've got 0.08. Okay, the next one is 0.1 times 0.5. There are only 1 in each formula unit, so I don't even need to do anything else. If you want to make it look pretty and in the same format, you could do the times 1. Next one is 0.12 times 0.25 is 0.03. This one is another multiplier by 2, so 0.06. And your last one is 0.15 by 0.3, which means you've got 0.045 times by 1 is 0.045. Okay, and we're looking for the greatest number, so then it's just, can you read things properly from what you've scribbled down? A. Question 25. I genuinely feel for the last couple of questions that we're being relatively nice to you. So you'll notice that I've pulled the bond enthalpies data from this. This is obviously what you need to use. The covalent bond in a halogen molecule can be broken to produce halogen atoms when exposed to light of appropriate energy. So that's basically your free radical stuff. The bond enthalpy is the energy required to break 1 mole of bonds in a diatomic molecule. Which halogen would require a minimum of 3.22 times 10 to the minus 2 kilojoules to break 1 covalent bond? Right, this is kilojoules per mole, and we're looking for how many for 1 bond. So basically, you just have to take each one. So let's start with fluorine. Fluorine is 159 kilojoules per mole, but I want per bond, so I'm just going to divide it by L. So you're 6.02 times 10 to the 23rd, okay? And I get 6.61 times 10 to the minus 22. Okay, I've obviously scribbled all this down already. Next one's chlorine. So that's 243 over L. And it gives me 4.04 times 10 to the minus 22. Okay, it's saying we'd require a minimum of 3.22. And I'm like, okay, chlorine at the moment is 4.02 times 10 to the minus 22. Bromine is 194 times over L, 3.22 times 10 to the minus 22. And iodine 151 over L is 2.51 times 10 to the minus 22. Okay, so you need 3.22 times 10 to the minus 22. There's your answer. And that's the paper. That's section A of the paper.